Welcome back again. Today we are going to discuss the solution to exercise problems of chapter 12. This was the first chapter of ring theory, I guess, and we discussed in this chapter a ring and some subring and examples also, and the types of ring and uh, certain classification based on the elements a ring has, like commutativity. When we say that a ring is commutative, when we say that an element is unit, or when we say that a ring is commutative with identity or a commutative ring without identity. So these are things we discussed in chapter 12. And in chapter 13, we discussed about integral domain and fields. So these are the things we have discussed until now. In chapter 12, we will be seeing the question based on ring and subrings. Of course, we may get certain questions related with units and identity. Okay. So let us start the discussion. I will give you a brief solution to the questions. Okay, let us see how much we can do today. And some questions, I guess, we have discussed in regular classes before. I think 5 or 6 questions, but let me, for the sake of completeness, let me recall them again. Question number 1 says that give an example of a finite non-commutative ring. And another example they wanted, that example of infinite non-commutative ring that does not have a unity. So these kind of examples, in fact, of a non-commutative ring, we can get in matrices, as I have told you before. So answer to the first question, do you remember finite commutative ring, finite commutative ring, finite. So it is finite, finite and a non-commutative, finite and non-commutative. Finite and non-commutative ring. So we can consider when it comes to non-commutative ring, we can consider this, the set of matrices, 2 by 2 matrices, okay. Because we want finite, so we can select here. This is in fact field, not, yeah, this is field. So we can consider it Zn, okay. We can consider Zn, and not exactly field, but we have seen, I think this would be prime in that case. But the thing is that here we are considering the element from Zn, okay. Do you remember Zn is field when? For what value of n is Zn is field? Forgot.
Prime.
Yeah, you can verify it. In a finite integral domain is a field. We studied a finite integral domain is field. Okay. Okay. So we have also seen for not for even for a prime, this is not going to be an integral domain. For certain primes, it is going to be an integral domain.
Yes, sir. When
Yeah. So not
when
for
p
all,
minus 3
it's
is
going to
divided
be
by
field.
4.
Yeah. So this n should be of the form something 4m plus 3, something like this. Then it is integral domain because it
Yes,
is
sir.
finite, so it is going to be a field. Okay. So first of all, this should be an integral domain. A finite integral domain is a field, you know. So that you should remember. Okay. Let us see the answer. If finite non-commutative ring, we can take this one. And if infinite, if you want infinite infinite non-commutative ring. So we can take M, set of all matrices of 2 by 2 type, and because we want infinite, And non-commutative, we can take the elements from Z. Okay. And they wanted, they are again saying that it doesn't have a unity. So it has unity. This is with unity. With unity. This is with unity because 1 0 0 1 is a
1001.
yeah. So can you give me an example where it is infinite and non-commutative, but without unity? M2.
सर Z का कोई भी NZ टाइम्स का कोई भी वो ले लीजिए सब ग्रुप.
Yes, yes. So this is certainly in this M2 to Z or M2 MZ kind of thing, where M is not 1. M is not 1. So, or in general, we can write like this, MZ, and you need to make sure that M is not 1. So this is a ring without unity. Without unity. Okay. Next question. The ring 0, 2, 4, 6, 8 under addition and multiplication modulo 10 has a unity, find it. So on that day we verified it. What was the value? Unity? I guess it was 6, huh? It was 6. Third question is that give an example of a subset of a ring that is a subgroup under addition but not a subring. So if it is a subgroup and not a subring, okay. So we know that any if it is a subgroup, okay. So what thing can stop it to be a subring? Okay. Do you have
Sir,
any idea?
yes sir. A
Yeah.
मल्टीप्लिकेटिव एसोसिएटिविटी या फिर क्लोजरनेस नहीं होगी.
Yeah, closeness of this set under multiplication, one thing. Another is associativity. Why it's not selected? Another is that it should miss the associativity. All right, associativity under multiplication. That is third thing. That is closeness under multiplication and associativity. And anything else? Because they are telling that a subset of a ring that is a subgroup. They are telling that this is a subgroup, but this is not a subring. So if it is a subset of a ring, they are taking subset of a ring and they are claiming that this is a subgroup. So certainly this subgroup is to be commutative. Hello.
Yes sir, under addition.
Yeah, under addition, this is going to be commutative because this is subgroup of a subring of a ring. Right? This is subgroup of a ring, and ring is
Yes sir.
commutative under addition. So we cannot say, okay, there is one more thing that under addition, because it is only subgroup, it is not commutative. So this can also be the reason. Okay. So based on these two, and associativity is a hereditary kind of thing. If a superset is associative, then subset is also going to be associative. That's all. Fine. And because this is subset, they are talking about the subset of a ring. So certainly associativity will be transferred in that subset. In fact, then the subgroup. Okay. So what else may be the reason? Only closedness. Okay. So in closedness, we can consider a ring of this form x square root of 2, or we can take any prime here in place of p in place of 2, and we can take x belongs to the set of integers. So we are considering this kind of set. And you know that when we take x square root of 2 and y square root of 2, we are getting xy times or 2 times of xy. Okay, so this is not a member of R of this set, so it is not closed. But under addition, this is a subgroup. Okay. So let us take another example. Let us take next question. Question number 4. So by example that for fixed non-zero element A and B in a ring, the equation can have more than one solution. So in case of this 2x equals to 2 in Z4, we can take solutions are x equals to 1 and x equals to 3. So there are two solutions. You know that if you put here x equals to 2, so we will be having a 6 in the left side and it will be reduced under modulo 4. So it will give us 2. But in the case of group, in a case of a group, when they are talking about the group, it means they are talking about the group under multiplication. Okay. In case of group, Ax equals to B has unique solution. Unique solution, and that is given by x equals to A inverse B.
A inverse B.
Yeah, because you know why we are able to write here, because this is a group under multiplication, and in multiplicative group, you know that multiplicative inverse should exist. But in general, in a ring, this is not the case. And then question number 5, theorem 12.2, and in this we have we are supposed to prove that inverse of elements, if exist, they are unique in a ring, and identity element also unique. Okay, so this we can take the proof from the group theory. So I'm leaving it. Question number 6. Question number 6 says that find an integer n which shows that the ring Zn need not have the following property. Okay, so it is telling that a need not have. It is not telling that have following property. So we need to find where this does not hold. Okay, these does not hold. So let us see. You know that because we have already read and studied more about integral domain. And integral domain, we have seen that there are no zero divisor, huh? Which means what? Which means that if a b equals to 0, if a b equals to 0, it means that either a is 0 or b equals to 0. At least one should be 0. If at all this is 0. Okay. So this we can relate. We can with the help of this we can get answer from for this one. Okay. The second part, B part. In fact, for the first part and third part also, uh, it is helping us to recall the example from where we can get. If it is the integral domain, then certainly a times b equals to 0 would imply either a is 0 or b is 0. Okay, so we need to, but we need to find non-example. Okay, the ring which does not have these properties. Okay, so that we need to find. It means we need to consider the ring which are not integral domains. Okay. Okay, because we have read the chapter number 13, we have discussed the chapter number 13, integral domain. So that's why we are taking here advantage. Otherwise, we need to search here and there. What would be the reason? Okay, so let us see. Question number 6, first part. We can take Z10, we can take Z10, and in Z10, 5 square equals to 25, and 25 equals to 5. So 5 square equals to 5 here, okay? But 5 is neither 0, nor it is 1. Are you getting what I am trying to tell you? Hello.
Yes, sir.
Okay. In the second case, if we take a integral domain, then this will hold, but we need where this does not hold. Okay. So for that
सर
we
Z6 ले लीजिए.
need, yeah. So जी क्या बोल रहे हैं आप?
Z6
Please.
ले लीजिए.
Z6, okay. Yeah, Z6 we have discussed. Yeah, 2 times 3, na?
2,3.
2 times 3,
Yes,
not
sir.
comma. Yeah, 2 times 3 is 6, and this is 0, but neither of them is 0. 2 is not 0, and 3 is also not 0. In C's part, they are talking about the cancellation, and the cancellation integral domain came just because of cancellation law. Because in a general ring, we don't have cancellation law because this is not a group in general under multiplication. So we don't have any authority to say that their cancellation law hold. But the thing is that when we talk about the integral domain where there is no zero divisor, so which is equivalent to having no zero divisor equivalent to the cancellation law. Okay. So another example here we can take maybe Z4, or you can try Z10 or Z6 also. Okay. Here we can take 4 times 2 equals to 0, and 2 times 2 in Z4 there are also, this also 0, this is also 0. Okay. So but thing is that if we I think I should write like this, na? I should write like this. Okay. Here 2, and in the left side we have 2, 2. Like here we have A, and A should be non-zero. So 2 is non-zero, of course. So this doesn't imply that 4 equals to 2. Okay, fine. So this is another non-example. So question is that is the n you found prime? Is the n you
No,
found
sir.
prime? So yes, it should be prime. It should be prime. So I think we are done. Okay, question number 6 done. So let us see next question. Question number 7. Show that the 3 properties listed in exercise 6 are valid for ZP, where P is prime. So actually we need to prove them in general. Okay, we need to prove them in general. Okay. So we know that in ZP, let us see the solution of question number 7. Let 0 is not an element, A is non-zero element of ZP, A is non-zero element of ZP. Then A inverse belongs to ZP, Z star P, let us
Yes, sir.
write.
ZP is a field.
Yeah, why? Because this is a group, huh? Because Z star P is a group. So if this is a group, so okay, so let us see them one by one. First part. The first part is A square A. This implies that because A is non-zero element, so its inverse exists. We can take product of this A inverse from the left. So we can write like this. So in the left hand side we have A, and in the right hand side we have identity. Let us write E or 1. Okay. So in ZP we find that first hold, this hold, this hold. Okay. What we were supposed to prove, either it is 0 or it is 1. Because A is not 0, so we have taken A is non-zero, so we are getting A is 1. Okay, next thing is that if a product of two element is 0, then either of them, one of them is going to be 0. So let us write A B equals to 0. Then A inverse and let us write like this. So this implies that B, if we write, we can write B as A inverse AB. All right. And therefore, A inverse and AB is nothing but 0. So this implies that 0 in the right hand side. So B equals to 0. Okay. So when A is non-zero, B has to be 0. Then third part, AB equals to AC. The same thing, because A has inverse, so we can take product as we have done in the case of group. So AC. So in the right hand side and left hand side, we are left with B in the left side, and in the right hand side, we are left with C. So B equals to C. Next question. So that a ring is commutative if it has property AB equals to CA implies B equals to C. So here cancellation, this is another type of cancellation. This is this element in extreme left and this is in extreme right. Okay. So in this case, we can have B equals to C. Sorry. Okay. So let us see how we can prove. This is number 8 number question. Given that R is commutative ring. R is commutative ring. Okay. So let us take let X, Y are elements of R. Then we claim what we claim X, Y equals to YX. This we need to prove. Because R is a ring, so R dot, that is under multiplication, this is going to be associative also. So therefore, using the virtue of associativity, we can write X times Y X equals to XY X. Is it okay? Okay, because of associativity. And now let us take some replacement. A equals to X, and then B equals to YX, and C equals to XY. So in view of this, this expression becomes, in place of X, we need to take A, and then in place of YX, we need to keep B. And here XY is nothing but C, and then X is A. Okay. And this implies that B equals to C by assumption of the question. Okay. So this implies that B is what? B is YX and C is XY. So this is this says that R dot is commutative. All right. Let us see next question. Question number 9. Question number 9, it says that prove that the intersection of any collection of subring of a ring R is a subring of R. So I think this is easy. I think we don't have any space here. Okay, let us see. So if they are talking about the collection, they are talking about the collection. Question number, I think ninth question. So we can take collection. Let Ri be rings. Okay, and let us take R as the intersection of Ri over I, intersection over I. Okay, suppose there are elements xy belongs to R. Okay, xy belongs to R. So this implies that x and y belongs to Ri for all I. Fine. And because Ri are rings, so therefore x, let us see, they are telling subrings or what? Let me see. And it's subrings. Okay. So let me write here subrings. Okay. Because they are subrings, so x minus y belongs to Ri, and x times y, this should be closed also.
Y belong to
Ri, and this should be true for Ri. And therefore, because x minus y and xy belongs to Ri for all I, so it means x minus I belongs to intersection of Ri. And x times y also belongs to intersection of Ri. Okay, so this proves that intersection is a subring. But union, we will see that need not be subring. Okay, so that we will see, and for that you can give example. Okay, let us see next question. Question number 10 and 11. Verify the examples 8 through 13 in this chapter as stated. So I think I should leave these questions. I have discussed already in the classes. Prove the rule 3 to 6 of theorem 12.1. And of course, this theorem we have proved in the class already. Already done. So they have been done in the class, and this you can verify. Example number 3, 8 through 13. Okay. And then question number 12, it says that if A, B, C be elements of a commutative ring, suppose that A is unit, then we need to prove that B divides C if and only if AB divides C. Question number 12. A, B, and C belongs to R, and R is commutative ring. And also I think A is unit. It is given A is unit. You know that we need to prove that B divides C. B divides C like this. B divides C. So if B divides C is meant what? That C equals to some K times B like this. So in the similar fashion, we have we need to also prove that AB divides C. It means AB C equals to some L times AB like this. So there are two parts we need to prove. If and only if, they are writing if and only if. Okay, let us see. So let us assume that let B divide C. Then how we can write? Then C equals to D.
Some A times B.
Yeah, D times B. Okay. For some D belongs to R. Okay. And then therefore we can write C as D, and then we can write A inverse because A is unit, and then B, and then we can write like let us write like this. And commutative, if it is commutative, then we can leave this also. We can swap them, so we can write D A inverse A and B, and this is done because this we can do because R is commutative. All right, and then we can take D A inverse and here AB. So C becomes DA inverse times AB, and conversely also. So this implies that AB divides C. Okay. Another part, let us assume just a minute. What there? No. B divides C if and only. Okay. So either we can go reverse side or no. Let us not sure about this whether we can go reverse side or not. So anyway, let us write this like this. In a ring, we need to be very careful, because they don't have unique solution. An equation. So let us assume let A B divide C. Then I think we can go reverse side also. C equals to some AB times D, AB times D, and this implies that C equals to because it is commutative, so we can swap these two. We can swap these two. So it we have AD times B like this, and this implies that B divides C. B divides C. Okay. So this proves the this 12th result. Okay. But in question number 13, they are saying that describe all subrings of ring of integers. I have told you already. Do you remember? Yeah, I think yesterday itself I told you. So they are talking about this ring. What are subgroups? In fact, if to be a subgroup, to be a subring, first of all, it should be a subgroup. So what are the subgroups of integers?
Sir,
I.
N Z, N belong
Yeah.
to Z
Yes.
positive.
Yes. The subgroup of Z are MZ. Okay. Uh, what they wanted? Describe all. Okay. Describe all subring. And because they are commutative, okay, and closed under multiplication and associative also, so they are going to be subgroup. ऐसा इसलिए भी हो रहा है क्योंकि जेड जो है साइक्लिक होता है ना, ऐसे क्यों इसके सबग्रुप ये ऐसे ही होते हैं? इट इज बिकॉज जेड इज cyclic, and so uh, its subgroups सबरिंग होने के लिए सबग्रुप्स तो होने ही चाहिए ना पहले अंडर एडिशन में. So its subgroups will be, so इसके सबग्रुप्स भी क्या होंगे? वो भी साइक्लिक होंगे, है ना? And are of the form m times z, like this. Okay. So let us see next question. Question number 14. Question number 14 and then 15 is there. 15th question ये ग्रुप थियरी में जैसे था, हमने एक बार करा रहा होगा, आई थिंक सिमिलर है, सो आई वोंट बी टचिंग इट. आप लोग देख सकते हैं इसको. 15 you can try. 14 let us see. M times AB, they have written M times AB 14. M times AB they are writing, and then they are writing M times, I don't know what they have written. I think A times MB or something like this. Let us see. Yeah, MA times B. MA times B, not this. And then in the right Another part is A m times B. A m times B. So same thing they have written in different way. And if we have been using all these because they were rings at least. Okay. So let m equals to 1. They are, I think they have considered m to be integer. Okay, an integer. So in case m equals to 1, then and of course without loss of generality, we can assume that m is positive. Okay, without loss of any generality. In case of negative, we have seen that minus 8 uh, times b, something like this. I think minus a in a ring. If we have seen this kind of example, minus ab. So even we are taking negative, there is absolutely no problem. We can take only positive and prove it. Okay. Let me write it completely. There is no loss of generality if we take m to be positive integer. Okay, to be positive. So we use mathematical induction. Let m equals to 1, then we are done. So let it is true for m equals to suppose k. That is, I'm writing first two part. First these two part. You can later on take other also in a similar fashion. So that is 1 times ab equals to 1 times a times b, something like this. Okay, so ab equals to ab. This is true. Okay, this is true. What I have written. This was true in case here. Okay, ab 1 times ab equals to 1a times 1a times b. 1a times b. Here we need to write like this. Okay, how we can write here that k times ab equals to ka times b, and you can write here also. Then later on you can take yourself. And also from here we have ab equals to ab, or we can write a1, that is 1 ab equals to 1 times ab, some like this. Okay, where they are keeping dot with m. Yeah, with m they are keeping dot with m. So this this dot should be here. Okay, not here. So now you can add them side by side. Okay, add them side by side. So in the left hand side together they k plus 1 times ab, and in the right hand side we have k plus 1 times a and b. Fine. So this implies that this, suppose let us name it as star. So this implies that star is also true for m equals to k plus 1. So by principle of mathematical induction, star is true for all n belongs to integer. Okay, n belongs to integer. M and n belongs to integers. Next, let us see the question number 15. I'm leaving to you. And question number 16, we can try, I think. Question number 16, what they are telling, m n minus a minus na. let me see. Let me write here. Or above here we can write. Okay. Question number 16. To prove this, we can to prove that we can prove NA plus N times A equals to 0. And for this, how we can consider? We can consider this means what? N copies of negative A. So we can write negative A plus negative A plus dot dot plus negative A. How many copies? N copies. N copies, and then plus here also N copies of A. So A plus A plus A and dot 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 plus A. This is also N copies. N copies. And let us then we can put together because they are element of a ring, elements of ring. So A negative A will give us 0, and then A negative A will give us 0. Okay, so this is going to be 0, and once it is proved, it means what? N minus A is equals to minus NA. So this was we were supposed to prove. Question number 17. Show that a ring that is cyclic under addition is commutative. So अगर cyclic हो जाता है रिंग ना under addition भी, तो भी वो commutative हो जाएगा. Interesting है. Interesting in the sense कि property of additivity is deciding the property of multiplicative commutativity. Interesting ना? अंडर एडिशन अगर साइक्लिक हो जा रहा है तो वो कम्यूटेटिव हो जाएगा. दिस इज इंटरेस्टिंग रिजल्ट. सो 17 okay, it is given that R is a cyclic. Okay, so let R be a ring, and because this is cyclic, so it should be generated by some element A. Okay, and under addition it is cyclic, so the elements in this ring should be of the form n times A, where n belongs to the set of integers. All right. Okay. So we can take any two elements. Let M, A, and N, A belongs to the ring R. Then we can take their product M, A, and N, A. And because this is cyclic, okay, and also we have seen in example, you see the exercise number 15. In exercise number 15, M, A, and B. So we can put them together, and we have here AB. Okay, so what we can write here? M times N, okay, and A square we can write like this. Okay, I don't think there is any doubt in this. So we can write Mn. Let us write like this AA. Okay, and therefore we can NA. Okay, because this is this. Okay, NA we can write. NA. Okay, we can write it as NM and AA. NM and AA. Let us see. MNAAB. Okay. Just not the way I think we should do something. Okay, let us see another way. This let us take NA and MA, and this we can write NM A square, and because NM are integers, so we can write MN A square. Okay, And this we can write in view of that result 15th, we can write it as m times a and n times a. Fine. So this is the thing. So NA and MA equals to MA NA. So it is commutative. Next, 18th, A belongs to the ring R, and they are defining a set containing those elements of the ring such that A times X equals to 0. So that S is a subring. Question number 18th, I guess, yeah, 18th. So in S, they have elements from R such that A times X equals to 0. So to prove this is subring, we need to take any two elements. So let us take X and Y belongs to R. X and Y belongs to R. So consider X minus Y, and let us pre-multiply it by A. And because multiplication is distributive over addition, so we can write it like this: X plus minus Y, and therefore we can write AX plus A times minus Y. Or we can write AX, and because this is a ring, so we can write A minus Y is equal to A times Y, negative A times Y. And because XY belongs to, this is not S, R, but this is S, okay. This is S, this one, okay. So this should be 0 and 0, and this is equals to 0. It means what? X minus Y equals to, no, X minus Y is also member of S. Is there anything left to prove that this is subring?
XY,
no? Okay. XY, okay, XY, then we can multiply it from left. Okay. So we can write it as, no. Let us write like this. AB, and then ABX, like this, okay. Bracket time is ABX. This is equals to A times BX, A times BX, and BX is 0. So A times 0 is equals to 0. Fine. So their product, or we can take XY also. There is no problem like this. XY, we are taking element XY now. XY, and then here we can take A. So we can write AX here and Y here now. So AX is 0, 0 times here. This is equals to 0. Okay, so XY belongs to S. You got it? I mistook the symbols, okay. And then let us see. Question number 19. The center, you can do it in the similar way. And describe the elements of M2Z that have multiplicative inverse. Question number 21, you need not to attempt because the direct product we have not done until now. Okay, it is not part. So this you can try. And question number 20th. In 20th, we can. Question number 20th. We can have example in matrices. Okay, in matrices, or so we can take element A, B, C, and D that have multiplicative inverses. So इसका multiplicative inverse कब होगा बेटा? Suppose we are taking A, इस matrix का multiplicative inverse कब होगा? एक तो ये नॉन जीरो हो ना, ओके, एक तो ये नॉन सिंगुलर हो, बट ये एलिमेंट्स कहाँ के हैं? ये एलिमेंट्स यहाँ से हैं, ठीक है. These elements are here from. So we need to choose them like AD minus BC is equals to either plus 1 or minus 1. Okay. I think we don't have time now. Question number 22nd. 22nd question, they wanted to find the units. So you can do yourself. I think we have talked about much about units. In this case, plus minus 1 and plus minus iota. These are going to be the units. Here also you have to find the units. So this is a polynomials, set of polynomials, ring of polynomials with integer coefficient, with integer coefficients. तो इसमें से किसके इनवर्स होंगे? कोई ऐसे पॉलिनोमियल लीजिए जिसका इनवर्स हो. अब इनवर्स भी कैसा होना चाहिए? This inverse should have integer coefficient. This should also have integer coefficient. So what kind of this should be? This should be equals to 1. That is okay. That is a px equals to 1 is the only element here which has which is unit multiplicative inverse. And in the similar case, determine here with real coefficient. Here integer coefficient, here integer coefficient के साथ में polynomial है. So इस केस में क्या होगा कि all those polynomials और function fx and gx such that क्या हो जाए, ये इनके coefficients जो होंगे ना इसके अंदर वो they will be the real coefficient. Okay, so this should be like this.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.